7 is going to be on partial fractions. And so you did work with partial fractions in terms of like the decomposition component. Sorry, got a little draw. That's what I'm trying to do. Okay. So you did work with decomposing partial fractions, like that should be in your kind of your background a little bit. And so what did decomposing fractions look like? So in your math 3 days, so if you were given something like this, you were asked to break it down into its linear factors and what it was equivalent to. So you would have this and you factored it, and then you had to solve and find the numerators that when you got a common denominator and added these together, you would end up with this single fraction. And so that's what we're going to be working with. And then why are we doing that? So it's because integrating something like 3 over x plus 2 is just using natural log, easy peasy, right? Versus trying to integrate something like that, you'd be like, complete the square, long division, what would I do? And so that is why we do the decomposing of our fractions. So we could be like, cake, it's natural log. So one thing I do want to warn you about is that we only do non-repeating linear factors. But there's a whole world out there that goes beyond that. And so it might be something you look into just a little bit. And so if you have linear factors that are repeating, then you have to look at something that's a lot more complicated. So for example, if this was like x plus 2 squared, you would have like a whole nother world that you would have to look at. And that would just be super fun. We're just not going to do it. And then the other component that we don't do as well is irreducible quadratic factors. So if you had something like x squared, plus 4, that doesn't factor to linear factors, then also you have to do something beyond what we're going to do in this class. So that's essentially what we're looking at. So if we have this like complicated fraction right here, how can we break it apart into its original pre-combined fractions and then integrate each of those independently? So, right, like easy to integrate, Ikes over here. Okay, so let's go ahead and take a look at this first example. So our first step is to decompose fractions. So we're going to have to think back to those days of honors math 3, like how did we do that, right? So how did we decompose? So I'm actually not going to just say decompose and expect you to remember how to do that. I'm actually going to go through those steps. Oops, that's an S for steps. Okay, so step 1. You want to make sure that you completely factor the denominator. Okay, so you're going to factor the denominator. Okay, and so I will, work through that over here. So when we factor this, so I'm not integrating right now, I'm just decomposing the fraction. So I have 5x plus 1, and then I want to factor the denominator. So that would be for x squared, x times x, and then factors of 2, that will also give me that 3x, are going to be 2 times 1. So there's step 1. And then we are going to set up the fractions that are pulled apart from each other. Okay, so you're going to factor the denominator, and then you're going to, show your setup of your fraction. And then I'm just going to say with split denominator, meaning we're splitting the denominator up. Okay. So what we have here is I know that one of my original denominators had to be x plus 2, and that was being added to a denominator of x plus 1, right? Because I have factors of x plus 2 and factors of x plus 1. So that means the original fractions that were added together had to have those in them, right? And what we don't know is we don't know what the numerators were, right? Like I don't know what was up here or up here, so that when I got common denominators and added, I would end up with 5x plus 1. So then we set that fraction up and whatever those numbers happen to be. And then from here, we're going to solve for A and B. And so how we did that is we solve it just like we would any other rational equation. Okay, so we're going to solve for a and b. And how we do that is we're going to multiply by the common denominator, and in particular, the lowest common denominator. So I'm going to multiply both sides of the equation. So I'm just going to bracket this out by my common denominator of x plus 2 and x plus 1. And as long as I do that to the left and the right side of an equals sign, right, an equation, I can do that, right? Whatever I do to the left, I do the right. And then I'm going to distribute that in. So when I multiply it in to this first one, the denominators will cancel, leaving with just the 5x plus 1. And then when I multiply it into the second fraction, so when I multiply it into here, the x plus 2 will cancel, leaving me with just the a and the x plus 1. And then when I multiply it to this one, the x plus 1 will reduce, leaving with just the b and the x plus 2. Okay. So then once I get to here, so after I multiply by my common denominator, then the next thing I'm going to do is I'm going to choose, not random values for x, but I'm going to choose values of x that are convenient, right? And the ones that we want to do are the ones that are going to be zeros, that create zeros. Okay. So we have two values that we're solving for, right? We're trying to solve for a and for b. So that means I want to pick two values of x. So the first one I'm going to choose is -1. And the second one I'm going to choose is -2. I do not have to choose those two numbers. I could choose any numbers in the world that I wanted. I could have picked 0 and 12. But I want to make it easy for me to solve. And so since I want to make it easy for me to solve, I'm going to pick whatever is going to make something turn into a 0, right? Because, woo, that's pretty dreamy. So if I let x equal -1, this will turn into 0. So that's why I'm going to choose it. And then if I let x equal -2, that will turn into 0. That's why I'm going to choose it. But again, I didn't have to pick those numbers. I still will get the same answer. This just makes it a world of difference, right? Just makes it that much easier to solve. So now I have to solve them independently. Like I can't put in -1 and then -2 at the same time. So I'm going to just do one thing at a time. So I'm going to replace all of the x's in this equation with -1. So I would have 5 times -1 plus 1, and then equals a times -1 plus 1, and then plus b times -1 plus 2. Okay, so all I did was replace all of the x's up in this equation with -1, and then I'm going to solve for one of the variables. So then this would be -5 plus 1, which is -4. And then -1 plus 1 is 0, so that would be 0a, which is 0. And then -1 plus 2 is 1, so that would be 1b. So then now I know b is equal to -4. So now I want to solve and do this all over again, and I'm going to replace x with -2. Okay, so I'm going to do the same equation, but replace x with -2. So that would be 5 times -2 plus 1 is equal to a times -2 plus 1, and plus b times -2 plus 2. So this would be -10 plus 1, which is -9. And then -2 plus 1 is -1a. And then that would just be 0. And then when I divide by -1, I would get a is equal to 9. Okay, so then now once I do that step, now I'm ready to go into the calculus component. So far, what I've done right now is not calculus related, but is math 3 related, right? So all of that right now was just kind of that algebra component. So now I'm ready to move on into the world of calculus, okay? So then for step 4, so then we're going to go back to that equivalent expression up above and replace a and b. So we're going to set up our integrals. using that equivalent expression. So using, I'm just going to call it the partial fractions. With A and B substituted for their number values. So again, these are equivalent, right? These are equal to each other. So the part that I'm going to be working with, though, is right here, because that's the piece I want to integrate. And so that's what I'm going to be working with. And so I'm going to replace. So instead of integrating this side, left side over here, I'm going to integrate the right side. So then I would have the integral of A, which is 9 over x plus 2. And then plus B, which is negative 4 over x plus 1. And I'll be integrating with respect to x. Okay. So now just to integrate each of those, I'm going to integrate them independently. I mean, I can do them all together in one step, but just for the sake of explaining, I'm just going to integrate both sides. And again, most of the time, so I'm going to separate my integrals. You don't have to, but now you're going to integrate. And almost every time, it's going to be a natural log. Okay, so we're going to integrate, and then usually it's a natural log pattern. Not every time, because there is that whole quadratic repeating factor component. Okay, so I'm going to split up my integral and pull my coefficients out. So I have 9 times the integral of 1 over x plus 2, and then minus 4 times the integral of 1 over x plus 1, and then dx. So I would do a rewrite. So this is a step that's not necessary. I'm just going to show it to you because I'm going to hope that we can branch into kind of a mental math step of that. So if I let u equal x plus 2, that derivative is 1 dx, which is what I have. So then that would be a natural log of x plus 2, and I don't have to worry about trying to multiply or divide anything over. And then over here, u would equal x plus 1, and then that derivative is 1 dx, which is exactly what I have. So then also a natural log, and I don't have to worry about trying to get, a u du set up. And there you have it. Okay, so we're going to do a couple more of these. If you feel pretty good about it, you might want to go ahead and try the next couple on your own, and then just check to see if you have the right answer. So I'm going to start with this 5 minus x, and in the denominator, factor that out. So 2x squared would be 2x and x, and then to get a negative 1, I know it'll be 1 times 1, and then one of the numbers needs to be positive, one of them negative. My middle term is positive, so I want this to be positive and this one to be negative, because that would give me positive 2x minus 1x, which is 1x. So then I would have a over 2x minus 1, and then plus b over x plus 1. And then multiply by the common denominator. So that's like just the original like factors that you have, right? And then distribute that through. So I would have 5 minus x. And then here the 2x minus 1 will cancel, leaving the a and x plus 1. And then to the last fraction, the x plus 1 would cancel, leaving b and 2x minus 1. So again, I'm going to pick random values of x, but not so random. So what would make this 0 is negative 1. And then I'll substitute that in. So I'm going to do a little mental math at the same time I do it. So I'll have 5 minus negative 1, so 5 plus 1, which is 6. And then here, negative 1 plus 1 is 0, so that'll be 0. And then here I have 2 times negative 1, which is negative 2, and then minus 1, which is negative 3. And then divide by negative 3. So if I did that too quick, you may want to hit pause and then substitute in negative 1 for yourself, and then just kind of check that as well. All right, so then now I want to do another value. So again, I could do any number I want. right? So what would make this 0 is actually 1/2. So I could choose 1/2 if I wanted to, but that seems kind of like, do I really want to plug 1/2 into all of this? And I don't. So I'm just going to let x be 0 this time. Okay, and so again, 1/2 would work. You would get the same answer. 7 would work, and you'll get the same answer. So I'm going to just use 0 because that's how lovely is 0. So I'll replace x with 0. So 5 minus 0 is 5. And then a times 0 plus 1, which is 1, so 1a. And then here I'll get 2 times 0, which is 0 minus 1, which is -1. So a, and then -1b, or a minus b. And I already know b is -2. So a double negative, so that would be a positive. And so then I would get a is equal to 3. Okay, so just again, one more time, I could have picked anything. So like if I, just to show you that I really could pick anything, like let's say I picked 7. Should I pick 7? Why not? So if I'd chosen 7, I would get 5 minus 7, which is -2. 7 plus 1 is 8. 7 times 2 is 14, minus 1 is 13. And again, I know b is -2. So that would be -26. Add that over. What is that, 24? And then if I divide by 8, I would get a equals 3, right? So absolutely not a step I needed to do, but that's just to kind of show you that I really could pick anything I want, and I'm still going to get the same answer, well, so provided I did my arithmetic correct. All right, so now that I've done that, I'm going to go ahead and set up my integral, so that I'll do that over to the side here. So I'm going to be integrating a, which was 3, so 3 over 2x minus 1, plus b, which is -2 over x plus 1. And then I'm going to do my rewrite, so I'm going to pull that 3 out. And that -2. So over here, you might want to write out the u and the du because the derivative is not just 1. So I would let u equal 2x minus 1. And then that derivative would be 2 dx. So I don't have that 2, so I need to divide it over. The other one is fine though, right? So I have the 3. I'm going to divide out the 2. And then this would be u to the -1, which is just natural log of 2x minus 1. And again, I know I'm skipping steps, but hopefully because we've done a fair amount of natural log, that's not too bad for you. And then over here, the derivative of this is 1 dx, so I don't need to do a substitution. So that would be just the natural log of x plus 1. And now if you need to, actually write out those steps for the natural log substitution, I highly recommend that you actually do that. And that's strictly just so that you have, something to kind of go back and look over your work, and there's not so much being held into your head, that you actually have something to physically look at to follow your steps a little bit cleaner. I know I skipped a bunch of steps, but hopefully you didn't. Hopefully you wrote those out for yourself. Okay. All right, so let's go ahead and take a look at the last one here. So this one is a definite integral, so we have limits, but we're still going to do the problem the same. So the first thing I want to do is factor that denominator. And this, again, might be a good time to press pause and then just skip ahead so that you can kind of check, did you do that piece right? So I would have 2x squared is 2x and x, and then I know my factors are 1 times 2, and I want to get up to 5. So I want the 2 to multiply to the 2x, and then both positive. And then split up your fraction, and then multiply by your common denominator. So the 2x plus 1x plus 2 would cancel, leaving just the 3 behind. And then distribute to the next one. And then this time the 2x plus 1 would cancel. And then on the last one, the x plus 2 cancels. And then choose your values for x that you want. So I'm going to start with -2 because that's a nice easy 0 to work with. So there's no substitution here, so that'll stay 3. And then -2 plus 2 is 0, so that would go away. And then I would have b times 2 times -2 plus 1. So that would be -4 plus 1, which is -3. And so b would equal -1. And then pick anything you want over here. So again, I could pick a fraction to make that 0, right? That would be -1/2, but I'm going to take a hard pass on that and choose 0. So replace x with 0, so I'd have 3 equals, and then 0 plus 2 is 2. And then this would be 2 times 0 plus 1, 0 plus 1, which is 1, so plus b. And then I also know b is -1, so let's use that. So that would be -1. Add the 1 over and divide by 2. So then let's go ahead and do our integral here. So I would have the integral of a, which is 2, over 2x plus 1, and then dx, and now plus the integral of b, which was -1, over x plus 2, and then dx. And then this time, I'm going to use my 2 over here. So you're going to see this. Okay, so you can pull the 2 out, but I can see that the derivative of 2x plus 1 is 2. So that means I want that to stick around, don't I? And then the derivative of x plus 2 is +1, so I am going to pull that -1 out. So again, I'm just trying to go through that idea of you don't always have to write out your UDU. It's okay that you do, but you don't have to. So here if I see that my u term is 2x plus 1, and then chain rule, that derivative is 2dx. So this is perfect, right? So then this would just be the natural log of 2x plus 1. So it's possible that you have, like a UDU component where this would be u to the -1 du, and then which is just the natural log of u, which goes right back to that, right? And then this is the derivative is 1 dx, which is perfect. And so that will also just be a natural log. And then plus c. And then one thing I do want to point out, just as a reminder, because they do this a lot of times on multiple choice, is they'll use properties of logs to combine these. And so an alternate answer to this would be just division. So 2x plus 1 over x plus 2. So that is also another possibility, so that when you're subtracting, you can just combine them through division. And that's it.